So this is where we left off the last time we were together, and we were in the middle of talking about resistance, which is basically um, kind of not allowing as much electricity to go through as you might expect. So the amount of electrical resistance depends on four different things. One type of thing, the amount of electrical resistance depends on the type of material. For example, if you had gold wires in your house, electricity passes through gold very, very easily. It provides very little electrical resistance. And then there's things like silver and copper, and then there's aluminum. Aluminum provides a little bit more electrical resistance. So if you had wires that are made completely of aluminum, there will be more electrical resistance. If you had wires that are made of graphite, it does conduct electricity, but not as well as aluminum. And aluminum not as good as copper, and copper not as good as silver, and silver not as good as gold. Maybe that's why you've seen high-priced electronics. They usually have gold tips on the end of their wires to conduct the electricity a little bit better. Another thing is the length of the conductor. The longer the conductor is, the greater the resistance. Again, think of it a little bit like water. If you put a garden hose that was only, let's say, 4 or 5 feet long, and you hook it up to a spigot and you turn it on, the water's going to flow out of that garden hose very, very easily. But let's pretend, on the other hand, you take a garden hose that is 3 kilometers long and you hook it up to a spigot and you turn on the spigot. The water's not going to come squirting out the end of the hose very quickly. It's because there's a lot more resistance. It's the same thing with electricity. You can see that these high tension wires down here, um, they provide very little electrical resistance because they're usually very, very large wires, kind of like what you see down to the left. So since they're large wires, they provide very little electrical resistance, and there is a long distance for them to go. And since there's a long distance, there is some resistance because of the distance, not because of the size of the wire. Also, the width of the conductor, and that's basically the size of the wire. If we look down here, we've got different gauges of wire. We've got 20 gauge, 18, 16, 14 gauge. The lower the gauge, the thicker the wire. And certain houses have to have a certain gauge. For example, it would be illegal for me to put 20 gauge wire in my house because I normally have up to 15 amps going through a breaker. 15 amps going through 20 gauge wire would cause that wire to heat up and eventually catch on fire. So I have to put in at least 14, sometimes 12 gauge wire through my walls. So the thicker the wire, the less resistance there is. The thinner the wire, the more resistance there is. So if you try to pass a lot of electricity through a wire like this, it's like trying to hook up a small um, garden hose to a fire hydrant. As soon as you do that, that garden hose is going to explode. Same thing with this wire. If you hook this up to a high amperage power source, that wire is just going to burn up. And the last thing is the initial voltage. So in other words, the greater the voltage, um, the the less resistance there's going to be. So actually, the more resistance there's going to be. I'm sorry. So think of it as the amount of push. So if there's a lot of electricity being pushed through a wire, there's going to be some more resistance through the greater the push. So which type of metals have the least resistance? We already talked about that. Usually the really expensive stuff like gold and silver. Which wire has the greatest resistance? That would be the 20 gauge wire because it's not very thick. And why do transmission lines have high resistance? That's because they're so long. If they were shorter and you lived really close to the power plant and the electricity only had to travel 1 or 2 miles to your house, there'd be very little resistance. So that brings us to Ohm's law. And Ohm's law is the mathematical relationship between voltage, current, and resistance. And there's a formula that goes along with Ohm's law. A good way to think of it is, here's this triangle, in which case the V stands for voltage, A stands for amperage, and then this, I don't know what the Greek sign is for that, but that's resistance. And you could say voltage equals amperage times resistance. Or if you wanted to figure it out another way, you can manipulate the equation by using a little bit of math magic. So voltage equals current in amps times resistance. So here's the other ways you can mess with the equation. In this case, it would be the amperage equals voltage divided by resistance, or resistance equals voltage divided by the amperage. Now, chances are, on one of my tests, you will most likely not have to work with this equation. However, it is certainly good to know, and this graphic down here kind of sums everything up. Ohms is the resistance. So we measure resistance in ohms. So this ohm is basically trying to resist, trying to slow down the amperage. The voltage is the potential electric energy, and it is trying to push more electricity through. Amperage is the amount of flow. Notice that the amperage is being forced through by the voltage, but resisted by the ohms, or the resistance. That kind of just sums things up, and this is silly because here's watts and ohms, and we're going to talk about watts in just a little bit. Let's talk about circuits right now. A series circuit has only one path for electricity to flow. And in this case, this diagram also has it backwards. The electricity flows from the negative and goes all the way to the positive. But in a series circuit, it's a lot like the older Christmas lights. Let's just suppose I take this bulb right here and I actually remove it and I leave the circuit open. Will the circuit work if there is an open spot here? It won't. Same thing if this bulb were to be broken or if this bulb was burnt out. That would mean the whole circuit would stop working. Same thing with these old Christmas lights. If one light bulb is broken, if one light bulb is burnt out, if one light bulb is missing, the entire string of Christmas lights will not work. So that's a series circuit. Series circuits are relatively unpopular, especially in things like houses and things like that. When any part of the electrical path is broken, electricity will not flow. Then there's parallel circuits. Parallel circuits are a little bit better. Parallel circuit, it's a circuit that provides more than one pathway for electricity to flow. Houses, schools, and all that, they're wired using parallel circuits. Take a look at this battery here. In this case, the electricity should be flowing from the negative, and it's going here. And let's just suppose that this globe, this light bulb, is burnt out. Can the electricity take another path? It can. It can travel this way and then make it all the way around. So in other words, if one light bulb is burnt out, it's no big deal. The electricity can still flow just fine. Same thing with this over here. The electricity, think of it as like a ladder. In this case, even if this light bulb were to burn out, that's not the end of the circuit. The circuit is still complete even if this light bulb burns out, which means the electricity just says, oh, well then I'll travel this way, go through this light bulb, come back here, and then make it all the way back to the battery. That's a parallel circuit. And a parallel circuit is when even if one light bulb or one part of the circuit is not working, the circuit is still complete. And let's talk about fuses and fuse breakers and electrical safety real quick. So this is a fuse. This is an old-fashioned fuse. This is a circuit breaker box. My house used to have these old fuses. This is a 15 amp breaker. Like I said before, the wires in my house are rated to carry 15 amps. That's why I have a 15 amp breaker. If I had a 20 amp breaker and 19 amps are going through my wires, the 20 amp breaker would not work. The wires in my wall would catch on fire and my house would burn down. That's a problem. So in this case, since my wires in my wall are rated for 15 amps, I would want 15 amp breakers. These are also kind of the switch breakers. This is the update. That way you don't have to go to the store each time you break one of these fuses, and you don't have to replace it each time. Notice the thickness of the wire down here. The thickness of the wire actually determines the amount of amperage that it can carry. I normally, like I said, put 12 or 14 amp wires through my house, usually 14 for lighting and 12 for anything else, which carries 20 amps. So in this case, I could have a 20 amp breaker, and that would be perfectly fine. Why might someone want to limit the amount of electricity flowing through a circuit? Well, In this case, it just depends on the wire that you have in your house. No one really has 2-gauge wire because that's really, really huge, heavy to work with. Most people have 12 and 14-gauge wire in their house. So you want to limit the amount of electricity through your house because of the size of the wire. Remember, the smaller the wire, the greater the resistance there will be. So let's talk about electrical power. Electrical power is the rate at which electrical energy is converted into other forms of energy. In other words, electricity is great, but the only reason why it's great is because of what it can do for you. It converts itself, well, machines and light bulbs and whatever will convert the electricity to light, or convert it to sound in a radio, or convert it to images in a television, or convert it to light waves in a microwave, or convert it to heat in a crock pot, or convert it to kinetic energy in a blender, a drill, or a reciprocating saw. So wattage is basically the rate at which the electricity is converted into its form. And electrical power is measured in watts. So take a look at this. Different things have different starting watts and then running watts. For example, let's take a look at a blender down here. The blender starting watts is 850 starting watts, but it's 400 running watts. Maybe you've noticed this before sometimes in certain houses. Whenever you turn on something that's going to provide a lot of electricity, maybe a toaster, maybe a blender, the lights around it blink. Like the lighting overhead, it might dim for just a second and then the lights start working again. That's because in order to get this thing started, it needs more wattage, where it uses more wattage, and then eventually it levels off at around 400 once everything gets moving. So different things use different amounts of wattage. And I suppose here's a good question. Why is it so good to replace something like a refrigerator, even if a refrigerator uses relatively low wattage? Well, it's because your refrigerator is on all the time. Your blender is not on all the time. Your TV, hopefully, is not on all the time, nor are your lights if you turn them off like you're supposed to. And the amount of power that you use, of course, is rated in kilowatt hours. That's how it's measured. Each type of device you ever buy will have information about the wattage and the voltage listed on it. So let's talk about AC power and DC power real quick. AC power is basically alternating current. This infographic right down here kind of sums things up. It's basically you go from negative to positive, negative to positive, negative to positive, and it keeps going back and forth, back and forth. Direct current is a steady flow of electricity. And I know what you're thinking. You're thinking, well, I thought you said current is a steady flow of electricity. Yeah, it kind of is, especially from a battery. But the stuff that comes out of the electric circuits in your walls, that's actually a little bit different. That's an alternating current. Think of it like this animated GIF down here. You can see that the water will flow one way and then it'll flow back, and it'll flow one way and it'll flow back, and it'll flow one way and it'll flow back. In this case, this would be an alternating current. It turns out Edison was a huge fan of direct current, but one of the drawbacks of direct current is it doesn't travel very far through wires. Nikola Tesla was a huge fan of alternating current. There was a war of the currents that happened, I don't know when it was, but there's a war of the currents. It turns out Nikola Tesla's alternating current won, and that's what we currently use right now, is alternating current. How can we prove that the light we have is an alternating current? Well, if you use a regular incandescent light bulb and you look at it under really slow motion, it turns out that the light blinks on and off and on and off and on and off. And you say, I can't see that. That's because electricity runs at 60 hertz. In other words, 60 cycles per second. So your light bulb turns on and off 60 cycles per second. And you can't see that. If you use some of the new LED lighting on Christmas trees, maybe you've noticed that they seem to blink really, really quickly. That's because you're using alternating current. Well, we're getting to that point. We're about time's up again. And when we come back, I'll direct you to this video. And we only have a few more slides after this, so we'll go from there. Stick with me. Thanks.